All right, so we're going to try to create a video here that allows you to understand the sodium carbonate, sodium bicarbonate titration. Okay, so this is a little bit difficult to explain and difficult for students to understand, so we're going to try to go through it slowly. Looking at initially just the net ionic equation for this titration, the net ionic equation. All right, so we start off with carbonate ion, CO3 2 minus, and we're adding hydrogens, right? We're adding hydrogens. And the result is, and this is what we do in parts A and B, right? The result is ultimately H2CO3, right? And so we see that it requires 2 units of hydrogen. Okay, that's what we're doing in part A and B. And this is the net ionic equation. To help us feel comfortable, we'll just draw the molecular equation as well. Okay. Right, so in the molecular equation, if we don't get rid of the spectator ions, we have Na2CO3 combining with 2 HCl's to form H2CO3 and sodium chloride. Right? And in recitation, we said that because we're doing the titration in such a way that we're adding HCl in the burette here, right, little by little to our sample of Na2CO3, then this reaction doesn't occur all at once, right? It occurs in steps where initially the Na2CO3 combines with 1 unit of HCl and creates NaHCO3 and 1 unit of NaCl. And then if you continue to add hydrogens to this solution, you get the NaHCO3 combining with another HCl, right? If you keep adding those hydrogens, and you'll get the H2CO3 and another NaCl would be produced. So this top one here is how we write it in class. And this is kind of this top one, an initial step where the sodium carbonate is converted to sodium bicarbonate. And then this is a second step where the sodium bicarbonate is converted to carbonic acid. All right? So we have 2 indicators. We have one indicator, the phenolphthalein. The phenolphthalein will change color once all of the carbonate has been converted to bicarbonate. Whereas the methyl orange, it won't change color until all of the carbonate is actually converted not just to bicarbonate, but to carbonic acid. So the phenolphthalein won't change color, the methyl orange won't change color until this reaction has completely occurred. Whoops, we forgot a 2 on there for that sodium chloride. So that reaction has come to completion. So we have 2 tools. The phenolphthalein allows us to see when all of the carbonate is converted to bicarbonate. And the methyl orange allows us to see when whatever we started with, whether it's sodium carbonate or sodium bicarbonate, has been converted completely to carbonic acid. And so that's why in parts A and B, right, when we perform the calculations for parts A and B to determine what the concentration, the molarity of HCl per liter of the HCl solution, right, when we perform that calculation, We start off with 0.2 grams of Na2CO3, and we go from grams of Na2CO3 to moles of Na2CO3, and from moles of Na2CO3 to moles of HCl. Now, I'm kind of giving away the secrets in this video. So it doesn't matter, though, because if you just copy and don't understand, we'll find out in the final, because you're going to have to do this sort of thing in the final. So you have to be sure you understand how to do it so that you don't lose a ton of points on the final. Okay? So don't just look at this and say, oh, I just have to copy those values down and I'm done. You have to understand what's going on. Okay? And we can put our liters of HCl required to do the titration here, right? And then that gives us our units of molarity. And we said that the molar ratio here was either going to be 1 to 1 or 2 to 1, depending on whether we use the phenolphthalein. That'd be a 1 to 1 ratio, right? 1 sodium carbonate per 1 HCl, because the phenolphthalein turns color once all the carbonate's been converted to bicarbonate. But it would be a 2 to 1 ratio for methyl orange, because methyl orange won't change color until everything has been converted to carbonic acid. All right, so that's part A and B, right? So this is back to our molecular equation, just the the net ionic equation. The net ionic equation, just the carbonate getting 2 hydrogens to form carbonic acid. And for this to come to, to indicate that this has come to completion, this would be our methyl orange. But in the unknown that we're working with, we actually start with a mixture of Na2CO3 and NaHCO3. We have some sodium chloride in there, but that's just filler. We're going to find out how much of that there is simply by taking the difference of our sample mass from the found mass of those two. So, because sodium chloride is not being titrated in the reaction at all. Okay, so our initial mixture, this is our unknown. Our initial mixture, unknown mixture, is a mixture of these 3 things. And again, going back to our net ionic equation, because all we need to relate in our net ionic equation is the moles of carbonate, because that will relate to the moles of sodium carbonate. The moles of carbonate combining with hydrogen ions being converted to HCO3 minus, right? That's the first step. And then the HCO3 minus being converted, adding a hydrogen ion, and then being converted to H2CO3. So that's what will happen to our unknown as we add hydrogen ions in the form of HCl, right? First, the carbonate will take a hydrogen and form the bicarbonate, and then all the bicarbonate will take a hydrogen and form the carbonic acid. The phenolphthalein will turn colors once all the carbonate is gone. The methyl orange will turn colors once all the carbonate has been converted to bicarbonate and all the bicarbonate has been converted to carbonic acid. Okay? So then, how are we going to determine how much of these unknowns there are in the sample? Well, to determine the amount of this stuff, the phenolphthalein is good for that, right? Because it's going to turn colors after all of the carbonate has been consumed. So we can use the volume of HCl required for the unknown solution to turn the phenolphthalein color. When the phenolphthalein turns its color, then that tells us that the carbonate has been consumed and shows us that the molar ratio between the HCl and the carbonate was equal. Okay? So we could perform a calculation to determine how much Na2CO3 we want grams there was in our sample by finding the volume of the HCl solution necessary to change color with the phenolphthalein, right? That's going to be in liters. Let's say it was 0.09 liters, which is 9 milliliters. Okay, and then we can compare that to the molarity of our acid. So liters of the HCl solution to moles of the HCl solution, 0.099, let's say. So, this depends on whatever your calculation was. Moles per liter of the HCl solution. And then, from that, we can go from moles of HCl to moles of Na2CO3, right? And then go moles of Na2CO3 to grams of Na2CO3. Right? The molar ratio here is 1 to 1 because the phenolphthalein will turn color when each carbonate has a hydrogen ion. All right? Now, how do we determine, that's hopefully more straightforward, but how do we determine the concentration of the bicarbonate, the sodium bicarbonate? Okay? So, for the sodium bicarbonate, we have to think about what's happening in our mixture. So here's our container that we are unknown. It was in some water. And we have the CO3 2 minus in there and some HCO3 minus in there. All right? Those are the two things we have in there to start off with. This is what I'm going to draw the CO3 2 minus ion. And then I'm going to draw the HCO3 minus ion, because those are the things we start with. We have this mixture, we start with it, and then we start adding hydrogen ion. Now, once we start adding hydrogen ion, the only species of these two that are going to take hydrogens is going to be the carbonate ion, because the bicarbonate ion already has a hydrogen, so it has a weaker affinity for that hydrogen ion, whereas the bicarbonate doesn't have any hydrogen ion yet, so it will take all the hydrogen ion until it becomes bicarbonate. So that's the first thing that happens. All of the carbonate that's in solution is converted to bicarbonate. All right, and again, the indicator here that we can use to indicate that this process is done is the phenolphthalein. All right. Now, once all of the carbonate is converted to bicarbonate, now we have in solution bicarbonate. This is the bicarbonate that we created. This bicarbonate I'm going to call bicarbonate original. And that's what we want to know, how much original bicarbonate was there in solution to start off with. Well, the volume necessary of HCl to convert the carbonate to bicarbonate, right, will also be that same volume. If you keep adding HCl, it'll be the same volume necessary to convert the bicarbonate to the carbonic acid. Right? So let's say this took 0.07 milliliters to convert all of the carbonate to bicarbonate? Well, it's going to require that same amount, 0.007 milliliters, for example, to go from the bicarbonate that you created to the carbonic acid. And all of that has to happen before the original bicarbonate can then be converted also to carbonic acid. We're going to actually draw its own molecule here. Okay? So what we have here is a mixture of carbonate and bicarbonate. We added hydrogen ions. Initially, the hydrogen ions converted this carbonate to that bicarbonate. Then those hydrogen ions went to convert that bicarbonate to carbonic acid. And then all we had left over was the original amount of bicarbonate. And then we could keep adding HCl until all of that was converted to bicarbonate. Now, once all of that is done, once all of the bicarbonate from the original and from the carbonate that we initially started with, once all of that is converted to carbonic acid, then the methyl orange will change color. Okay? So let's say, for example, to get all of this stuff to carbonic acid, it required 28 milliliters of solution. Whoops, this isn't 0.007 milliliters, that's 0.007 liters, which is the same as 7 milliliters. 7 milliliters. All right, so if the whole process required 28 milliliters to get the methyl orange to change color, and we want to know how much of that 28 milliliters was necessary to change our original bicarbonate to carbonic acid, then what we have to do is from this 28, we need to subtract the amount that was required to get this carbonate to bicarbonate and the bicarbonate from the carbonate ultimately to carbonic acid. So we're going to need to subtract these two values here, and we can find that value by how much it took to convert the carbonate to bicarbonate with the phenolphthalein. We need to subtract those two values, right? And the leftover was the amount of acid necessary to convert the original bicarbonate to the carbonic acid. Okay? So this 7 milliliters, that would be the value that we would use to identify the concentration of the carbonate ion, or the sodium carbonate. The 28 milliliters was the methyl orange color change, but we have to subtract the volume that it required, because that 28 included not just the amount for the original bicarbonate, but the amount for the original carbonate to go to bicarbonate, and that bicarbonate to go to carbonic acid, and then the original carbonic acid to go to bicarbonate. So we have to subtract those two units, our phenolphthalein, twice, and the result would be the volume, 14 milliliters, would be the volume related to that original bicarbonate, and thus the original sodium bicarbonate. So when we want to identify the grams of sodium bicarbonate in our initial sample, we start with our volume of HCl in liters, which would be 0.014 for this scenario, right? We go from liters of HCl to moles of HCl. That's your hydrogen chloride's molarity that you found in part A and B. Moles of HCl to moles of NaHCO3, and then moles of NaHCO3 to grams of NaHCO3. the molar ratio here, because we're subtracting the amount necessary for those two, it's going to be back to a 1-to-1 ratio, because all we did is we took the bicarbonate to the carbonic acid. So that's just 1 proton necessary. Getting the grams of the bicarbonate and the grams of the carbonate, right? Grams of the sodium bicarbonate and grams of the sodium carbonate. Subtracting those two from grams of sample, right? So grams of sample minus grams of NaHCO3 minus grams of Na2CO3. That's where we could get our grams of NaCl. And that grams of sample was 0.2 grams, right? Everybody should have started with something very close to that. Okay, hopefully that helps people recognize. I'll say it one more time, and hopefully you understand what's going on. But essentially, the titration occurs stepwise, where the carbonate is converted to bicarbonate first, and then that bicarbonate and whatever original bicarbonate was in solution to start with is then converted to carbonic acid. The phenolphthalein is used to identify the amount of carbonate because it will change color at a higher pH when all the carbonate is gone. The methyl orange is used to identify when all of the carbonate and bicarbonate has become carbonic acid. And so we can subtract 2 units of the volume for the phenolphthalein from the volume of the methyl orange. And that will relate to us the original amount of bicarbonate in the sample. All right, hopefully that helps.